PhD in France and Italy, I was working on the formal verification of hybrid automata. And at some point, I did an internship in Los Angeles for Toyota. And when I arrived at Toyota, people told me, oh, it's very interesting what you're doing, but we use symbolic models. So there are these very complex models with not well-defined semantics. And they told me, your techniques are useless for these kind of models, right? So what we care about is mostly about like testing. And so from that point on, I started working on a relaxation of the formal verification problem, which is just testing, meaning that how to run smart simulation of these complex models in order to find bugs and discover bugs. So this is to say just that since I started working at Berkeley, I focused mostly on formal testing. Okay, so I'll define the problem now, and I'll show you what I'm working on. So what I'm going to present is not like a super technical talk. I'm not going to speak about one paper in particular that we wrote, but I'm going to give you an overview of the topics that I worked on in the last 2-3 years. And if you have more technical questions, please stop me. I'll be happy to reply. So essentially, another important thing is that all this work is not done just by myself. So I've been involved in all these works, but there are many people working with me, and there are some PhD students, Daniel, Shamona, Shamyu, Alex, and then the various advisors of the PhD student, Kurt Coiter, Alberto Sandrani, Centelli, and Sanjit Sesha, who's also my advisor. Okay, so let's get started. I'm going to talk about testing closed-loop systems with machine learning models. So, as background, what do I mean by cyber-physical system? So usually cyber-physical systems are described as systems characterized by the integration of computation and physical processes. So what does it mean? It means that there is a physical part of the system, imaged like a robotic arm, that interacts with the real environment. And then there is a computational part. So there is like a computer, and there are some numerical calculations. Okay? So some examples are, as I said, the robotic arm, or the domain in which I'm working directly is automotive. So like a self-driving car. Okay? So there's a steering wheel, there are wheels, there are doors, and there is a computational side. There is a computer that tries to understand the environment. So lately, what happened is that there has been a rise of machine learning and artificial intelligence. So sometimes these two terms are interchanged. So what do I mean by machine learning? I don't know if you have heard about it, but it's actually an old branch of computer science, which is nothing but applied statistics. People who work with machine learning, you hate me for this, right? But essentially, instead of having a problem and writing down a program to solve the problem or an algorithm, what happens in machine learning is that you have a family of algorithms, you show a bunch of examples to the algorithm, and then the algorithm tries to learn the relationship between input and output. Okay? So I don't know if you've ever heard about neural networks and all this kind of stuff. So what happens is that a lot of cyber-physical systems now are integrating machine learning. So for instance, self-driving cars, instead of programming motion planners or controllers, what they do is they collect a bunch of pictures and trajectories for cars, and then they show them to a deep neural network, and the computer learns by itself to solve some problems. The problem is that many times these algorithms are able to solve very complex problems, but there are no formal guarantees on why they work. So in principle, in average, they work very well, but we don't have any guarantee. And so you can imagine that if you apply this system in safety critical systems like a self-driving car, we might want to verify, or at least be very sure that the algorithm is going to work. For instance, if we build an object detector, so like we plug to a camera a piece of software that detects people, we will have to be sure that whenever there is a picture of the person, the computer is going to detect that person, right? Because we don't want to kill people. And so my work, essentially, is about giving a cyber-physical system with the machine learning module, how can we analyze it, how can we debug it, how we can improve it once we find the bug. Okay. So the problem here is that classic formal methods are a bit tricky to be used. And in this initial part of the talk, I'll try to convince you that there are many challenges with verified AI, is how we call And why? So traditionally, formal methods can be summarized like this. We have a model of our system, we have a model of the environment, and then we have a specification that characterizes the correctness of the system, right? And hopefully, we have a magic box that is our formal method, our formal technique, in which we provide the composition of our system in the environment, and we give also our specification. And hopefully our magic box is going to say, yes, the system composed in this environment satisfies the specification, or maybe not. And hopefully we can also provide a counterexample. So by counterexample, I mean an execution of the system in that environment that does not satisfy the specification. Okay? So like you have a C program, you write down invariant, you have to be sure that the program satisfies the invariant. Or you have an hybrid automaton, you have a reachable set, you make sure that the algorithm does not reach the unsafe regions. Okay? So what's the problem with cyber physical systems with machine learning models? So number one, at the system level, we have to deal with very complex systems. So neural networks are a family of machine learning algorithms that are used to solve very complex problems. So one example of a neural network is AlexNet, which is a very famous architecture. And you can imagine this neural network as a composition of 650,000 nonlinear functions parameterized. And there are something like 60 billion parameters in this neural network. And so you can imagine that usually formal method techniques struggle with the dimension of the system, right? So many times they don't scale very well. So there is no hope to apply classic reachability analysis or whatever you want to functions with billions of parameters and thousands of nonlinear dynamics. Okay. Another problem is that we have to deal also with unstructured data. So for instance, pictures. Suppose we want to test, as I said earlier, the fact that whenever there is a human, we want to detect a person in a picture. Well, the input of this model is going to be the picture space. And if you consider all the possible combinations of pictures, you're going to have a very large number, right? So even the input space in which your hypotheses are huge. So we suggested that maybe there is a need for new methods for abstraction and modular reasoning. Rather than taking a network and hoping to send out a checker, maybe we have to do something smart. So the second thing is the model of the environment. So all these systems, they have to interact with very complex environments and agents. So suppose that we want to model, we have to have a model of our city in which we want to verify our self-driving car. So in this case, I show you three pictures in which there is a fake car in a real billboard. Okay. So suppose you have trained your model to detect cars in this case. If our model detects a car on the billboard, is it correct? Is it correctly detectable or not? So is it the environment in which the system operates are very complex and very not problem. Another example is vice versa. So you have a real car with a fake environment inside. Right? So imagine you're driving your self-driving car, and the self-driving car doesn't see the logo of the truck here. You don't make those frames, faces in top of heels. And then this is just a joke, but I found also the combination of the two. Like this is a real car with a fake environment with a real car inside. So there's like nested complexity of the environment. Anyways, maybe also in this case, we need a new way of representing environmental scenarios. Okay? And so at the end of this talk, I'm going to show you how we deal with the representation of scenarios and how we deal with environments. And lately, finally, which is probably this is my favorite problem with this problem, is that it's very difficult to write down a formal specification that characterizes the correctness of the system. So if I have a hybrid automaton, for instance, I can say this is my unsafe state, right? Unsafe area of the state space. But in this case, especially when we have perception tasks, how can we write down a logical formula that captures the correctness of the system? So I'll give you an example. Suppose I train my network to detect cars. Okay. In the first picture, we have a car, and hopefully we want our system to detect this kind of cars. Right? On the other hand, suppose that now we're driving in the desert in Nevada, and we find this hippie car, which is a giant snail, right? In this case, it's going to be very difficult to capture these kind of vehicles with the formal specification. Right? So even if I describe a car is composed by wheels, windows, and so on, I think the description of the car doesn't fall, I mean, this car doesn't fall in the classic description of car. And finally, again, this is another joke. Even if we describe a car, there is a semantic abstraction of what we mean. So, like in this case, someone said, put a sticker on the car that says, this is not a car, this is a piece of art. Like so, also in this case, this is just a joke to say that it's very difficult to semantically describe what a car is. And this problem also applies for any perception task. So you can also think about audio recognition, speech recognition, text translations. So in this case, classic formal specification languages might not be a good choice. Okay. So in our approach, we actually have worked on these three components: on system, on environmental representation, and on specification description. And in particular, we had worked on a relaxation of the formal verification problem. As I said at the beginning, we work just on testing. So meaning that we are not going to formally verify a system, but we are happy just to find one counterexample. So just one execution of the system that does not satisfy such specification. Okay, so the talk is structured following these three ideas: specification, system, and environment. And I'll start with the specification aspect, and I'll show you the trick that we use to impose a meaningful specification on our model. Okay, so a running example that I'm going to use during this talk is an automatic emergency braking system, which is composed by the following modules. So suppose that we are modeling a car in which there is an automatic system to brake, and we have a model of our car, so like the dynamics of the car. And like to this car, there is a controller that is essentially the brake. So this guy is going to slow down the car. When? Well, whenever the neural network detects a car in front of us that is too close under a certain pressure. Okay? So there is a camera in the car. The camera takes pictures. We take the pictures, we feed the neural network. The neural network is going to estimate the distance, for instance. And whenever the estimated distance is closer than 30 meters, the controller triggers a braking action. And we keep the distance between us and the preceding vehicle. Okay? So the goal, of course, given a model like this, is to brake whenever an obstacle is too close. And so we want to avoid a crash with the car in front of us. So there are two ways to impose to characterize this goal, right? One way is to say never collide. We don't want to collide. And we can say the distance between us and the car in front of us must be larger than 0, always. Right? This is one way to characterize this goal. The second way to characterize it is to say, I want my neural network to always correctly detect the distance between us and the car. If this is correct, and we are sure that the controller works, then the whole system is going to work. So this is an important difference. Why? Because if you remember earlier I said it's very difficult to predicate over perception tasks, right? So like in this case, it's going to be very difficult to say whenever there is a car, I want to correctly detect it. But on the other hand, we can achieve the same goal just imposing a quite simple formula or a quite simple constraint over at the system level. So over the distance between us and the preceding vehicle. Does that make sense? Yeah. And so this is all this story is just to tell you that instead of focusing in this work on specifications that predicate over the modules or machine learning modules, what we do, we impose specifications at the system level, so at higher level. We relax, somehow we hide the real problem. But later we are going to focus also on the testing of this part. So essentially we are going to test this part, hoping to find a counterexample at the system level. So we hide the problem of specifying something on the neural network on the perception task. We're using the system level, and we test the whole thing or more. Okay. And so the idea is how do we test these modules when we have specified specification at the system level, right? So the idea that we had, we developed this work that we call compositional classification, in which instead of testing the input for the physical system and the input of the machine learning modules, what we do, we essentially understand when the neural network is crucial for the specification we have imposed at the system level. We gather information, and then we do target testing. But I'll try to simplify. I'll try to explain that one. So suppose that the idea is not all inputs that are going to be a problem for the neural network are going to affect the specification at the system level. So suppose we don't want to crash, okay? You can imagine that this is a very simple example. If the car in front of us is going faster than us, okay, even if the neural network fails, it doesn't mean that we're going to crash against that car because it's going faster than us. This is a very simple observation, but it tells us that instead of focusing on all possible inputs of the neural network, maybe we can focus just on those that combine with the specific condition of the statistical system will lead the system to falsify our specification. Okay? And so the strategy that we develop is, at the first step, we analyze the cyber-physical system, gather information on machine learning flow. So for instance, if I notice that whenever the car in front of us is closer than 30 meters, for instance, I know that a misclassification might affect the correctness of the controller, then it makes sense to generate pictures and analyze pictures of cars that are just 30 meters close to us, right? It doesn't make any sense to find misclassifying images in which the car is 200 meters far away from us, right? Because we have time to slow down and we don't classify the specification of the system level. So once we have gathered information about the machine learning model, we can use this info to perform target analysis of the neural network, for instance. So as I said, we know that between 0 and 30 meters is a crucial distance, so we are going to generate pictures of cars that are just between 0 and 30. And then finally, once we find these classifying images for the neural network, we can combine it with the input space of our statistical system and perform target classification there. So I'll show you an example now that clarifies this point. Suppose that the input space of our cyber-physical system, as I showed in the toy example at the beginning, is the initial velocity, the relative velocity between us and the car in front of us, which is the difference between our speed and the car in front of us, and the initial distance, okay? And suppose we had a formal specification, as I said earlier, that predicates over the correctness of the system. Like in this case, always the distance between us and the car in front of us to be larger than 0. So here, the red points are combinations of speed and velocity, such that no matter what happens, we are going to crash against the car in front of us. I can slow down as hard as I can, but because of the laws of physics, I'm going to crash against the car. So, to understand this graph, if I pick a point here, in the corner here, this means high velocity and very small distance, right? So it means that I'm very close to the car in front of me, and I'm going really fast. So here, I can slow down as strong as I can, but I'm going to crash against that car, right? So the neural network, we don't care about what the neural network does. There's nothing to do. We're going to crash. On the opposite, up here, we have a lot of distance, like 60 meters, but we're going really slow, almost close to 0. And so here, for our specification, it means that also in this case, even if the neural network fails, we have enough time to slow down. There is always a combination of points, a control input that is going to be safe for, with respect to our specification. Now, what is interesting is this region here. So this is a collection of points that are potentially safe. So they do satisfy the specification, but a misclassification of the neural network might affect this point. So these are the points such that if I pick that particular combination of speed and distance and the neural network fails, there might be a crash, okay? And so essentially what we do, if we identify this area, then we can just generate pictures of cars in distance between 30 and 60 meters, and hopefully find misclassifying images for the neural network that then combined with this speed and distance are going to falsify our specification. Okay, so the plot that I'm going to show you is actually a real input space for a simulated model that we had from a collaboration with Toyota, and I'll show you later something that's in this one. The question is now, suppose that we identify the sub-region of the input space. How can we generate pictures that are going to fool the neural network, that are going to be misclassified by the neural network? Okay, and this is what I'm going to talk now. So ideally, so maybe I'm oversimplifying here, but the problem of the problem of generating pictures that are misclassified in networks is a kind of open problem which is a lot of work about adversarial machine learning, it's called. Essentially what you want to do, given an input, usually you want to alter the input in such a way that the neural network detects something completely wrong. Okay? Like I don't know if you've ever seen these works in which there is a panda animal, they flip 2 pixels, and then the neural network says it's the duck with confidence 99%. So here, our work is slightly different because we don't start from an initial picture, but we want to find the semantically correct picture. So like, if I know that I want to generate a picture of a car at distance 55, we want to generate a picture of a car at distance 55 such that the neural network does not see the car. Okay. And so what we did is instead of reasoning at a pixel level, like with the usual, as they usually do with machine learning, we decided to rely on image renderers, realistic image renderers, or simulators. And the idea is this one. So instead of focusing on pixel level, as I said, imagine that we have a picture space in which we focus just on realistic modifications. So for instance, we have a picture generator in which we can choose the distance, the position of the car on the road in the X. We can choose the brightness of the car, the picture, sorry, and then how far we can push the car far away from us. In this case, we can just perform testing and we can focus on this abstraction of the picture space, which is 3-dimensional, and you can see it as the input space of a simulator or a picture renderer. So simplifying the input space, the picture space with this abstract input space, what we can do, we can pick a point in this 3-dimensional space, we can give it to the to the simulator. The simulator is going to generate a picture, and then we can feed the neural network. And we can ask the neural network, is there a car or not? Do you see a car or not? If the neural network says yes, we are happy with that point. So we know that that point corresponds to a picture that is correctly classified by the model. But maybe keeping sampling all the input space, we are going to discover pictures that are not correctly classified by our neural network. So an important point here is that notice that there is no specification over the neural network. Somehow the specification is hidden inside the generation of the picture. Since we build the picture, since we generate the pictures, we know that in all the pictures there are cars. And whenever the neural network says, no, there is not a car, we know that that's a misclassification. Okay. This is a naive observation, but notice that we don't have to write down specification of correctness of the neural network. We just know how the pictures are built. So an important question is, suppose we want to test the neural net. How do we sample this input space, right? How do we discover the corner cases? How do we discover the features that are not correctly classified? So what we did is to experiment with different sampling methods. So this table shows you essentially on this axis here different sampling methods. So like a very stupid one is uniform random. So I just pick a point randomly from the input space and generate a picture and see whether the neural network correctly classifies the features or not. Another one is, for instance, low discrepancy sampling methods. They're also called quasi-random. And essentially, they, differently from uniform random, they fill in the space faster. So essentially, they converge towards the coverage of the input space faster than uniform random. Or other techniques, for instance, can be active sampling, so like cross-entropy. In this case, we pick a point, we give it to the neural network, and then we observe the prediction of the neural network. If the neural network says, this picture, maybe there is a car 50%, then maybe we can update the probability distribution of the input space, and then we can keep sampling in a direction that is more likely to be misclassified. Okay? So here it's like an active loop in which we observe the prediction of the neural net and we update our probabilities. So what happens is that there isn't a best one. So if we consider, for instance, a sampling speed, so the speed with which I can determine a sampling point, uniform random is the fastest one, right? You just randomly pick one. But if we want an insurance over the diversity, so I want to find samples that are as diverse as possible, I don't want points to be too close to each other because otherwise I'm going to have to reach too similar. Then low discrepancy is the best one because we are sure that we filling the space nicely. On the other hand, if we want to find the counterexample, just one, as fast as possible, then maybe cross-entropy is the best one, because we gather information about the neural net, and every time we exploit this information, treating the neural net as black box. Okay, so different comparisons, different sampling techniques depending on the goal. So I'll show you some results. In the beginning, I told you that we had a model of an automatic braking system, and essentially it's a simulated model plugged to a neural network built by Google, and it's called Inception V3, and it's like a state-of-the-art neural network. And in this chart, essentially you can see the sampling, the abstract space that I showed at the beginning. So here, this is the x coordinate of the car, this is the z coordinate of the car, so how far you push away the car, and this is the brightness of the picture. So the red points here corresponds to pictures that are not correctly classified by the neural network. So the point here corresponds to a picture that if you give it to the neural net, is not correctly classified. And here there are green points. I don't know if you can see the green, but these are correctly classified pictures. So all this red area is the cluster of misclassifications. So why does it happen? Because whenever the car is far away, it becomes very small, and the neural network doesn't see the car anymore. So this is not very surprising, right? And also it's not very important for us because, as I said earlier, if the car is far away, we have a lot of time to slow down, right? So it's not a problem for our specification. But if you notice here, so yeah, the misclassification of this picture here might be not of concern. But if you notice here, there is a single point here. There is an interesting corner case. And this corner case corresponds exactly to this picture here. And in fact, if we take this picture and we plug it to a simulated model with the distance of this picture combined to some velocities that we have from the chart, earlier chart, then we discover the simulated model generates a trajectory that does not satisfy our specification, our state specification. Okay? So this is just to show you that with this systematic sampling and testing of the neural net, we were able to come up with one single feature, kind of hidden also, this cluster of green points that leads the system to misclassification. Okay? So I'll show you more results also. This is earlier, I kind of cheated because the neural network that I showed you is built by Google, and it's a general purpose neural network, meaning that the network has been trained to detect cats, dogs, houses, whatever. So what we did next, we took a neural network that was specifically trained for self-driving purposes. So this neural network was trained just to detect cars. It was built just to detect cars. And it's called SqueezeNet, and it has been developed at UC Berkeley. So what we did here, we did exactly the same experiment in which we changed the x position of the car, we changed the y position of the car, and here this is another parameter actually. But so in this case, blue points are points that correspond to pictures that were not correctly classified, while red points are high confidence, so the neural network is very sure that we will count. And also in this case, it's nice because we can find an area which we call blind spot, and if we take these points and we superimpose them on the background that we use to generate these features, we can identify an area in which if we place a car here, the neural network is not going to see. Okay? So it's quite dangerous, and also we nicely discover a way to analyze this neural network. So here are some examples of pictures that correspond to this input space here. So here, this is exactly the same background, and if you put the Fiat 500 here, the neural network doesn't see. And there are also some interesting cases, like this case with the Toyota Prius. Whenever the car is very close, the neural network doesn't see, which is very dangerous, right? And other times, also this case is a visual over there. So, okay, stupid joke, making less. The Fiat 500, for some reason, is very difficult to be detected by neural networks, maybe because of the shape of the car, which is not, it's hardly observable in the US. There are few cars. And so I call the Fiat 500 the first stealth car for self-driving purposes. Okay, so once we find these counterexamples, what do we do with all these counterexamples, right? So we are happy we found the bug, we classify our system. Is there anything we can do? So the idea, we did a work in which essentially we analyze all these pictures that we generated that are not correctly classified, and we put them in what we call error tables. So if you remember, we had a lot of information about the picture that we generated, like the color of the car, kind of background, the orientation, the XY position, and so on. This is an oversimplification of an error table where we can gather all the information. So one thing is to analyze this error and try to find the recurrent patterns of this feature. So we could say 90% of the times in the classification, it was a white car driving in the forest. And another thing we can do is to do what is called augmentation of training set. So essentially, we have a training set for our neural network. We generate counterexamples, and we can take some of the counterexamples and stick that in the training set and retrain the model. So we can teach the neural network from the errors that it did. Okay? So this technique is called augmentation, and usually standard augmentation works like this. You take some picture of the training set, and you apply some transformations. Like for instance, you change the brightness of the picture, you rotate it, and so on. But here, it's slightly different because we are generating new pictures from scratch. So these pictures are not variation of pictures that already exist in the training set, but are new pictures built from nothing. And so, as I'll show you later, the neural net was able to learn much better from counterexamples. So, okay, very quickly, the scheme is like this to augment the training set. We have our image generator, okay? We can plug our sampler, we feed the model, and then we ask whether the car is correctly detected or not. If the car is correctly detected, then we keep sampling another one. But if we discover a picture in which the model not correctly detects the car, then we can store this picture in what we call an augmentation set. We can analyze these pictures in the error table, and we keep moving until the augmentation set is large enough, or maybe until we reach some confidence threshold over the input space. And once we're happy, we can just retrain our neural network and also analyze this error to provide explanations. Okay? So quickly, I'll show you some comparisons with techniques that already exist, just to convince you that this stuff works. So we have the model, we generate some counterexamples, and what we did, we split the counterexample in two sets, one for testing and one for augmenting. And we took the original model trained on this set, and we tested on our test set. And there are two metrics to measure the accuracy of the model. They're called precision and recall. So essentially, the higher these values, the better. Okay, for the model. So the model has like 61% precision, 75% recall. What we did, we took the original model and we applied standard augmentation. So as I said earlier, there's some pictures, split them, crop them, and so on. And it works in the sense that the model improves in precision and in recall. But whenever we use our counterexample guided technique, you can see that, for instance, with the low discrepancy sampling method that I mentioned earlier, you can go from 61% to 71%. So it's a big boost in precision. And recall up to 87%. So just adding few targeted features, the model learns a lot, and it's able to improve the accuracy quite a lot. Okay? So I'll skip the next slide, which is actually a study in which we took a group model, and then we reapply the scheme that I just showed you to see whether it makes sense, whether we can find counterexamples, like to see whether we reach a situation point. And actually we do. And it's harder and harder to generate counterexamples. If you're curious, I'll show you later. Okay, so we're almost at the end. And the latest part, it's about the modeling of the environment. So how we generate these pictures, how complex they can be, what kind of simulation we can use, and so on. And I'm going to talk about a recent programming language we developed, and it's called Cynic. And the idea is to have a programming language that can be used to specify a kind of scenario you have in mind, and then the language is going to generate pictures for you. I'll clarify this one. So what I showed you so far are just toy examples. As you remember, there is an input space of 3 dimensions like exposition, variation, and brightness. But in reality, what we do, we use very complex simulators. And actually, the very first work that we did was to use a video game called GTA 5, a hacked version of a video game, with very good graphics. And the input space of this video game is very large. So, for instance, you can choose the car model, the location of the car, the orientation, the number of cars, the background, time, weather, a lot of parameters. So what's the problem? if you remember, if you use random sampling and a sample a point even in this 9-dimensional space, the chances of building a scene that makes sense, that is realistic, are very low. Probably the car is going to lay down on a tree, it's going to be upside down, the car is not going to be on the street, facing the wrong direction, and so on. Right? So the larger the input space, the harder it's going to be to build a scene that makes sense. And so it's very hard, as I said, to generate input scenes. So what we did, we decided to write down a scenario description language that is essentially, in few words, is a probabilistic programming language defining distributions over scenes. And this is just a fancy way to say that we write down a program that is inputted and places some constraints over the input space in such a way that if we sample a point on the constrained input space, we are going to obtain a scene that makes sense and it works for our purpose. So for instance, I want to test my car, my neural network, and my system on Berkeley parked cars. So I want to generate scenes in which there is a car parked on the curb in a bad way. So this is a snippet of code that of our syntax that we designed. And essentially here we say pick an oriented point visible on curve. So even, you see, even in just a single line, there is a lot of stuff going on. So first of all, the point that we are going to sample is going to be visible from our perspective. It means that we are going to sample a point on the road, and then we're going to sample a point in front of us that is visible. So we really restrict the cone in front of us. And it's going to be on the curve. So it's going to be here, on the walk side, right? And then here we say just sample some bad angle for this car, maybe between 0, 1, 1 and -1 with some degrees. And then we say place a car at the left of this point, facing the bad angle. So with few lines, we can obtain a variety of pictures in which we have a car badly parked in front of us. And this is like a relative, this is much simpler than imagine like writing down linear constraints of the input space, which want to figure out all the positions of cars like in front of us, visible, with that angles. So the idea is once you write down a program like this, with a sampler, it samples point in this program, it feeds GA in this case, and then the video game renders pictures that are really cool. Okay. So one of the applications that we had for this programming language is to generate also hard cases. So what does it mean? When we collect images to train a model, there are some cases that are hardly observable in real life. So for instance, suppose you want to test the car, the neural network, in cases in which one car is partially occluded by the other one. If we randomly collect features like that, it's very unlikely to have in our training set features of cars in which one car is going to be exactly hidden by the other one. But if we had in mind this bad case, this hard case, we can write down our little program here, and then we can generate pictures that just satisfy this constraint, right? And then we can train our neural network, we can test our neural network with these hard cases, and then observe the behavior of the neural network on these hard cases. So for instance, here there are, you see, these are 2 cars, here there's another car, hidden by the other one, and so on. So these are examples of picture generated by language. And so finally, we can also do some reasoning on the neural net. So here is a picture randomly generated. But what happened is that the neural net detects 3 cars for some reason. Each bounding box is a car detected by the neural network. So here it says there is a car, and there is another car inside here, and then there is another car inside. That's pretty weird. So the question that we ask ourselves is that, what is the component of this picture that confuses the neural net? And so the idea is that seeing makes it easy to generalize along different dimensions. So we can ask ourselves, is it the car model? And so we take exactly the same scene, and we just turn off the constraint of the car model. And so we can generate exactly the same scene with different car models. Right? So you can say, what is the car model? Or maybe was it just that specific position, or just something about that scene? So we can take this picture, add some noise to the position of the car, and see whether the error is consistent. And then finally, maybe it was the background. Maybe it wasn't the car, it wasn't the position, it was just the background. And so we can just take that scene and teleport it somewhere else in the simulator and generalize from there. Maybe it was the shadow. Shadow is actually a real problem. Okay, so in conclusion, I show you mainly three things. One is a framework for system level generation of examples. And part of the trick is built around this convolutional neural network analyzer. So it's neural network analyzer that I showed you earlier. Another part that I showed you is what we do with these kind of examples. We can retrain the model using these kind of examples. And then finally, I also show you the recently developed language called C, generate these environments. So there are many things that we want to do now. All the experiments that I show you are actually built inside synthetic words. So everything works inside singular. But what about the real life? Because people say, oh, very nice. And what about real data? And so we already started doing some experiments in which we want to mix real and synthetic data. So maybe you have a model trained on real data, but then you can analyze it with a simulator and project it back to the real world. Another technique is to use what we call in machine learning domain adaptation. Essentially, train your model in synthetic world, and then you apply transformation to the neural network that adapts the model to the real world. This is hard, but it's doable. It works. And then finally, we reason just on pictures, but we are not constrained by the domain. We can also reason about more complex data like lidars, radar, other sensors for satellite accounts. There are many other data. Well, and then finally, also considering other neural networks, and then finally, this is a thing that many people ask us, is to see the language that I showed you, generate just static pictures, generate just a picture of cars still there. What we want to do is like dynamics. So, for instance, I want to say I want to generate a scene in which the car is driving for 50 meters, center speed, and then go. So what we are doing now is to develop like dynamics in this review. Okay, so that's it. Thank you very much for your attention. And please ask your questions.
Hello everyone, and really interesting talk, thank you. Actually, formal verification would be also interesting when you combine sensor fusion with LIDAR and radar, right? Because so you can have different perceptions and then have a description of that. And then you can make construct program check. Is that something you're thinking about, or?
Yeah. So this was a very first baby step towards applying for other indication of this class of models. Like companies many times are very interested in this problem called sensor fusion. Right? So the neural network says there is a car, the radar says there is none. Who's right? And so it's on the list of things to do. Trying to apply this technique to generate on purpose discrepancies along different sensors. So like LiDAR is going to say something, the radar is going to say something else, and so on and so on. Also because many times the problems are caused by the logics of the controller rather than the sensor itself. If you remember a few months ago, an Uber car killed the person. The sensors are all right, but the final decision was the wrong one. So many times the problem is not at the sensor level, but at the sensor fusion level. And so the idea is to apply these techniques to analyze the decision diagram. Yeah.
Good question. I mean, of course, these techniques can increase safety. I mean, if you're driving a car with sensor, for instance, people are looking at the phone and they're not aware that the car in front of them stopped at sudden. But for a completely automatic car, you find that there are not the sensors. Because that is new problem for the car. I mean, how are people going to accept this? So the fact that they are not, that is the worst case in any case.
Yeah.
So
yeah, it's a classic question, right? People say, would you trust a car that is not formally verified, right? That's right. Yeah. Can I summarize it like this?
So you have to use these techniques for instance for a nuclear equipment. So you know that almost never it will fail.
Yeah.
One.
So I usually reply like this. We had a conversation last night. So the thing is, we take flights all the time. Was the airplane formally verified? No. We write cars. They have a lot of software, right? Are they formally verified? No. Well, use them. So I feel like many times companies use. So one thing is the academic exercise, right? So the theory had a nice proof and see that something is correct, like abstraction. This is what mathematicians and computer science do. Another thing is product, what people buy or use. And usually in industry, it works like evidence testing. So I say, I drove my car for 1,000,000 kilometers. The car works. We can put it in production. People will like it. Something happens with the price. So my sense is people are very skeptical about cars, self-driving cars, because they are new. But as long as in a couple of years they forget about all the fears once they see them work, and then people will get used to it. I'm sure people the first time you take a flight you're a bit scared, but then second a bit nice, they're nice, forget about it.
But then the responsibility of a garage.
Right. Yeah, that's an interesting problem. I haven't had an answer, but I have a personal opinion. Yeah. I mean, even now, if the car doesn't work, if the brakes don't work, you hit the person, right? Who is responsible? Right? Is the car company? Is the engineer? Is the regulation and so on? And I guess it's exactly the same problem for self-driving cars. It's going to be the problem of the car company for the regulation. I think.
Yeah, that is the combination of the scientific. It should be actually monotone common and non-negative things for the weight. And in this model, you are assigning the weight to this weight is the same as threshold or is another. Okay. Awesome. Yeah, it calculates. Thank you very much. It's a kind of good stuff. Thank you. And about the Facebook, what the best financing?
It's up to you. If you decide to go and wait and see that